So at this point, we now have some, arguably far too many, formal structures that claim to model our intuition about infinity categories. But we promised to do some category theory with them, so how might that work? And in particular, we might ask, well, how can we do things like limits? And I mean, if we're thinking of whatever these structures that we've just been talking about are as categories, then we might ask questions like, what do limits and co-limits look like in those categories? Or can we form comma structures? Or can we do adjunctions? Or can we think about monads in this context, or Grothendieck fibrations, or toposes, or Yoneda's lemma, and so forth? So in principle, what I should do is I should go through, and I'm certainly not going to do it here, and explain to you, I mean, maybe pick one of those models, quasi-categories possibly, and explain to you how each one of these things works in that context. And essentially that process would be a translation process. I'd think carefully about how it worked in the category context, and then I'd try to see how I can translate it across into this more complicated context. And sometimes that works relatively straightforwardly, and we can see that the concept we get in this, in some of these strange models, is the same thing as the concept we started with. Other times that coding is a bit more complicated. But if you wanted, for instance, to find out how all of this was done just in the case of quasi-categories, then you might go to Jacob Lurie's famous book on higher topos theory, and he certainly explains all of these structures. So all of these structures can be found in that work. And he does in very great detail how those work just in the quasi-category model, not in any of the other models. So one question we might ask is, what model should we use? And certainly Jacob Lurie's decision was to use the quasi-categorical model. But what I'm going to suggest is that maybe we might take a different approach, which is, let's not pick a favorite model at all, or let's try and avoid picking a favorite model. Well, so when we started thinking about this many years ago, I was indulged because I'm an Australian category theorist. And so I was humored by allowing for the idea that we might try to do some of this stuff too categorically. So in Australia, I guess we've been worrying about two categories for many years, since the 1960s. And our primary interest, certainly in the 1970s, was to understand how category theory itself could be expressed inside a two category. So a two category is a category that has objects and has arrows between those objects, and then has arrows between those, which are called two cells. So we think maybe, I don't know, the category of categories is such a thing, because we have categories and we have functors, and then we have natural transformations between those. So we get some kind of two-dimensional category structure. And it turns out that we can develop a very great deal of abstract category theory just in the context of that two category of categories. And this is something that Australians are rightly proud of having done over many years. So maybe one approach would be to try and appropriate some of the things that Australians have been doing with two categories into this context. And I have a little cartoon that explains what we might want to do here. So the first thing you might think is, okay, well, I mean, that's great. Categories form, I mean, if I take categories and I take functors and I take natural transformations, they form a two category in a very natural way. But now if I take something like quasi-categories and I take the functors between those, and then I take the natural transformations between those, well, there's now all sorts of higher structure here, because there are homotopies between natural transformations and homotopies between those and so forth, because of course, everything's homotopies all the way up. So this is already starting to worry me at the point that we started to discuss this, because this means that I'm going to have to invent something called an infinity two category. So some kind of infinity categorical notion that is like our infinity one categories that we already don't really understand very well, and is also like these two categories, which maybe Australians understand quite well, but we might be a bit leery about generalizing them too much, and that sounds hard. But it actually turns out that we can do much better than this. We can we can at least make things a bit simpler by using a semi-strict model of such things. And in fact, the semi-strict model that we picked is a thing called quasi-categorically enriched categories. So they're strict categories that are enriched in the traditional sense of the word. Every single HOM is an object in some other category. And what's more, we have a composition operation which is strictly associative. And so these are relatively simple structures to define and to use, and certainly was something that we felt that we could deal with. And so we set to work. And technically speaking, what we got a thing called an infinity cosmos. So an infinity cosmos is, it's called that because the kinds of structures that they're modeled on were called cosmoi by Ross Street in the 1970s. And technically speaking, these are categories of vibrant objects enriched in the Joyal model structure. So that doesn't matter. What it means is that these are structures that have objects called zero cells, and they have arrows between those objects called one cells, and they have arrows between those called two cells. And then those two cells are related by higher homotopical information that's identical to the kind of stuff that we were talking about earlier on. And we can compose these things in two different ways. So we've got a horizontal composition that's just nice, straightforward, associative composition that we're all very familiar with. And then we've got vertical composition that is now done using this sort of quasi-categorical filling method. So at least in the horizontal direction, this is a nice, simple structure to work with. But in the vertical direction, it's still a little bit more complicated than we might hope for. But it turns out that for a surprisingly large range of purposes, it suffices to work in a quotient of this kind of structure called its homotopy 2 category. So the idea is that we kind of cheat a bit, and we do what we did with the infinity 1 groupoid right at the beginning. We take homotopy classes of things. So the homotopy 2 category of one of these cosmoses has, as its zero cells, the zero cells of the cosmos, and as its one cells, the one cells of the cosmos. But now what we do is for its two cells, because those had a complicated vertical composition structure, we take homotopy classes of those. And just as before, what that does is that now makes, once I take homotopy classes, I now get a nice, strictly associative vertical composition of these two cells. And what I get is I get a genuine 2 category. So anybody who's happy with genuine strict 2 categories should be happy at this point that they might be able to work in this kind of structure. Of course, interestingly, when I've given this talk in various other contexts to infinity category theorists, they're often very happy with infinity categories, but less happy with 2 categories, which I think is probably the wrong way around, but never mind. So this is a good old-fashioned 2 category, and we might ask the question, what do we get if we study standard 2 categorical structures in this homotopy 2 category? So a very quick case study I can give you is the case study of adjunctions. There's a very well-known notion of adjunction in a 2 category, and it's just given equationally. So to give an adjunction in a 2 category, for instance, in cat, we simply give a pair of zero cells, a pair of objects, A and B, and we give a pair of functors or 1 cells between them, U and F, and then those have to be related by 2 cells called the unit and the co-unit. So the unit goes from in this case, from the identity on B to U composed with F, and the co-unit goes from F composed with U to the identity on A. And notice that I put square brackets around this for the moment because our 2 cells in our homotopy 2 category are equivalence classes of 2 cells in the original thing. And then those things have to satisfy the famous triangle identities. And we know from experience in category theory that this is a complete characterization, algebraic equational characterization of adjunctions. And what's more, this thing satisfies all of the basic properties that we'd expect from adjunctions. So we can certainly play this game inside this homotopy 2 category, but by doing that, we might find that we don't get an interesting structure at all, except that in this case, rather remarkably, it turns out that when interpreted in various of the infinity models that exist, so all of those things, quasi-categories and Siegel spaces and complete Siegel spaces and Siegel categories and so forth, when we interpret this very simple notion of a junction inside the corresponding homotopy 2 category, we find that this notion coincides with all of the other notions of a junction for infinity categories that exist in the literature. And in particular, in quasi-categories, for example, such junctions are characterized by some kind of higher universal property, which can be expressed as a horn-filling property, which I won't explain, but which I've drawn in the slides for you later on. So that very simple equational notion translates into something that looks very similar to the kind of filling properties that we were using for describing composition in the quasi-category. And not only does this have a sort of basic version sort of at the level of the one arrows inside this structure that we might be familiar of, this looks very similar to the universal property that we usually have in a category. This is also comes equipped with higher versions. So there are versions of this notion of universal property that exist at all dimensions going up, which is a somewhat surprising thing because the equational definition that we gave inside the homotopy 2 category was somehow just two-dimensional. It was, I've got 4 things and I've got 2 equations, and it was very straightforward, sort of two-dimensional. But what we get out of that when we interpret it in these structures is we actually get all of these higher dimensional universal properties that we might want. In other words, this is the right notion of a junction, even although it's very, very simple in this. I mean, we've done some kind of terrible thing, which is we've taken an infinity 2 category, we've done massive damage to it by quotienting it out to give a 2 category. Then we've taken a notion that should not be at all related to a junction, in sort of infinity adjunction in this context. We've interpreted it and discovered it's the right thing. That's a kind of remarkable thing to do. It turns out that this is the right notion of a junction. And if we start doing 2 categorical proofs with these things, we get valid proofs about those junctions, of course, but we often get proofs that are much simpler than the infinity categorical ones that you might find in the literature on specific models. So, I mean, for instance, just looking at what adjunctions are, the definitions are complicated in a lot of those places, and what's more, the proofs with those definitions are complicated and sometimes a little bit unintuitive. So maybe I'll just conclude on saying how much can we capture in this way. So it turns out that we can capture theories of limits and I mean, this is sort of in this way working with these notions inside these homotopy 2 categories. So we can capture notions of limits and colimits, of comma infinity categories, of adjunctions, of growth and defibrations, of pointwise Kahn extensions, and we can do Yoneda lemma. So those are all things that reduce to essentially the 2 categorical proofs in those homotopy 2 categories. We can also, with a little bit of extra 2 categorical structure, handle things like pre-sheaf categories and toposes or infinity toposes in this context. You might also ask, what do we do about monads and monadicity? But it turns out that the monad study can't entirely be undertaken inside the homotopy 2 category because it needs a homotopy coherence result for adjunctions, which I can't explain in this talk. But once we have that, then we can emulate the proof of Beck monadicity, for instance. So Beck monadicity is expressible in the homotopy 2 category, and we can prove with this extra homotopy coherence result that it gives us the right thing, that it tells us what the monadic adjunctions are. And I think I'll stop there. I had hoped that I would tell you a little bit about type theory, but maybe I might encourage you to invite either Emily or I back to tell you about how we can do all of these things rather remarkably in homotopy type theory. So thank you very much, and thank you for your indulgence letting me speak for a few minutes too long.